First principles takes a bit of effort, but it lends itself to creating formulas because you're doing the same process every single time. So let's go right back to the constant. Well, we already proved what happens with a constant. Remember, it was a horizontal line, we ended up with 0. But let's just show that first principles work for that. Function x is c. Well, function x plus h will also be c because it's a constant. So if I sub that into our formula, I'll get c minus c over h, which is 0. So, okay, that confirms what we saw with a constant. The other one we worked out was a constant times x. When we had a straight line, we said it was going to turn out to be k. So let's use first principles to prove that. So function x is kx, function x plus h, kx plus kh, and sub it in, kx plus kh minus kx, kh on h, and we end up with our constant k, which is what we were expecting. So that just confirms what we already said. Let's now come up with a formula for differentiating x to some power. So x to the power of n. Now, in order to do that, I just need to remind you of some things. So, remember the difference of two squares. It was a minus b, a plus b. And then we did difference of two cubes. It turned out to be a minus b, a squared plus ab plus b squared. And in fact, difference of two quartics could be a minus b, a cubed plus a squared b plus ab squared plus b cubed. These difference of powers always start with a minus b, and then in the second parentheses, the powers of a are going down by 1, the powers of b are going up by 1. So we could generalise that to say a to the power of n minus b to the power of n would be a minus b. A would start with the power of n minus 1, powers of a are going down by 1. B is starting with the power of 0, but then they're going up by 1. And that would be our formula for a to the power of n minus b to the power of n. That's what I'm going to need to prove our formula here. So function x will be x to the power of n, which means function x plus h will be x plus h to the power of n. My first principles formula then gives me x plus h to the power of n. That's going to be a in this formula. And x to the power of n, which is going to be b. So when I do that factorisation, I'll start with a minus b, which is x plus h minus x. Then the powers of x plus h are going down by 1. The powers of x are going up by 1. Okay. Well, in that first parenthesis there, x plus h minus x is just h. And that will cancel with the h that's in the bottom of the fraction. So now I've got all these terms, x plus h to the power of n minus 1, x plus h to the n minus 2 times x, and so on and so on. But if I'm substituting in h approaches 0 now, then I've ended up with, well, the first term will be x to the power of n minus 1. The second term will be x to the power of n minus 2 times x. Well, that's x to the power of n minus 1. In fact, every single one of those terms will turn out to be x to the power of n minus 1. Question is, how many do I have? Well, let's go back here. When n was 2, I ended up with 2 terms in the parentheses. When n was 3, I ended up with 3 terms. When n was 4, I had 4 terms. So logically, when the power's n, there must be n terms in the second parentheses. So our formula then becomes n times x to the n minus 1. We've got a really neat formula. So what we're saying is whenever we're differentiating x to the power of n, all we've got to do is get that power, bring it to the front, and then subtract 1 from the power. We're done. So let's look at some examples then. Y equals 7. Well, 7 is just a constant. We said when we differentiate a constant, we get 0. Bang, done. Y equals 37x. Well, derivative is just 37. Y equals x to the power of 10. Well, now we know that's just going to be 10x to the power of 9. That power comes to the front, subtract 1 from the power. If we've got several terms, you just differentiate each individual bit. So 3x squared, well, when I differentiate 3x squared, the 2 is going to come to the front, but I've already got a constant at the front, I've got a 3. So we just multiply. So I'll end up with 6x plus 6. Now we will later see a rule that will handle things like this one, but for now we'll just expand it out. So 2x plus 1 squared will be 4x squared plus 4x plus 1. Differentiate each individual bit and we'll get 8x plus 4. If function x is x cubed minus 3, find the gradient function of 2. Be real careful with these ones. It's so easy to misread it and just think, oh, they're just asking me to find function 2 and substitute in 2. But if you see the dash there, no, they're asking for the gradient function. So we need to differentiate the x cubed minus 3, 3x squared. Now we substitute the 2 in, 3 times 2 squared, so the gradient function would be 12 at that 2. So back to what we were looking for. Let's find the equation of tangents. The curve this time it's a cubic. So y is 5x cubed minus 6x squared plus 2. Differentiate each individual bit. 15x squared minus 12x. Okay, there's our gradient function. We want at the point x equals 1. So sub in x equals 1. And we end up with 15 times 1 squared minus 12 times 1. Should be 3, shouldn't it? Yes, 3. We have a point. We have a slope. Let's put it in our point-slope formula. We have an equation of a tangent. So 3x minus y minus 2 is equal to 0. Find the points on a particular curve, x cubed minus 12x, where the tangents are horizontal. Now, why would this be an important question when we're curve sketching? So if you think about when a tangent's horizontal, that's only ever going to happen when when the curve turns around. So it might be going up and then come back down, or it might be going down, come back up. So the vertices, if you like. So they're quite important points to find. Well, there's my function. There's my gradient function, 3x squared minus 12. So really, this question is now saying, when is y dx equals 0? Now, in your setting out, explain yourself. Don't just all of a sudden magically go, oh, this equals 0 and find x. Explain why you're doing that. I'm doing that because I know that the tangents are going to be horizontal when that gradient function, or derivative, is equal to 0. So 3x squared minus 12 equals 0. There's going to be 2 possibilities. So it'll happen twice. Plus or minus 2. Be very careful where you substitute. I don't know how many times I've seen people go and substitute it back into the gradient function, and of course they get the answer 0. It's the y value we're looking for, so we want the actual function. We end up with negative 216 and 2 negative 16. I was kind of expecting that. Not so much the 16, but you see how the numbers match up? Because if you look at the original function, it's an odd function. So we should see some sort of symmetry there. There's this other line called a normal, which is quite important. And a normal is basically a line perpendicular to the tangent. So if I draw a picture here, there's a random function. That, of course, is our tangent. Well, the normal would be the one perpendicular to it at that point of contact. So that can be quite an important line to find. So you'll see questions where they ask us to find normals. So let's find the equation of a normal. Okay, it's a line. Finding the equation of a line, I need 2 things. I need a point, I need a slope. I have a point. I need a slope. Haven't got that, but I've got the function, so I can find the gradient function, in this case 8x minus 3. That'll allow me to find the slope of the tangents. So when x equals 3, we end up with 21. We don't want the slope of the tangent, we want the slope of the normal. So the slope we're looking for will be the negative inverse of that, minus 1 on 21. Point slope formula. Well, they're not nice numbers, but they are what they are. Put it in general form. There's the equation of the normal. All right. Finally, just some notes on when you're setting your solutions out. Okay. You are actually solving an equation when you differentiate. So the idea is what you do on one side of the equation, you do to the other. So when you have y equals x squared plus 2x, you have to think of this like it's an equation. And so I'm technically going to differentiate both sides with respect to x. So remember the different notations I said we could have. Here I've used the notation, I'm going to d dx whatever the function is. So in this case it's d on the left hand side, I'm differentiating y with respect to x. On the right hand side I'm saying I'm going to differentiate x squared plus 2x with respect to x. Well, dy dx is dy dx. And on the right hand side we get 2x plus 2. Reality is we go straight from the first line to this line. That's what we're actually doing. We're solving an equation. We're doing the same thing to both sides. The other important thing is to match the notation that's being used. So if I've got y equals x squared plus 2x, then I would say, oh, dy dx is 2x plus 2. Or I could go y dash is equal to 2x plus 2. If they said function x is equal to x squared plus 2x, then I'm not going to write y dash or dy dx. That's when I'd go f dash x is equal to 2x plus 2. So I'm matching the notation that they're using. And then the other one, d x squared plus 2x dx simply just has an answer. So it's 2x plus 2. So that's just a note on the setting out there. All right. Well, there's a few more questions. That'll keep us busy today. All right.